So we just learned about exponents, and now we're going to move on to polynomial functions, section 6.2 in your book. This is going to move pretty quick. If at any time you feel like you need to study more or take notes, or just pause anytime, just go ahead and pause and take your time. This is new material, so don't feel bad if you don't get the first time. This is the first thing that we have gotten to as a class where you haven't seen it before. So, a polynomial function has the form, and it's in green. It doesn't look too friendly, but I'm going to read it off just like it mathematically says. F of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot dot dot. And that's just, there could be a whole bunch of stuff in there. We're just leaving that out. Plus a sub 1 x plus a sub 0. This is the standard form for a polynomial function. In order for this to be a polynomial function, the following things have to hold true. A sub n cannot be 0. Exponents have to be whole numbers, not integers, whole numbers. In other words, we can't have negative exponents. And coefficients have to be real numbers. They can be negative. They can also be fractions, but they cannot be imaginary. So, a n through a 0, or a sub n through a sub 0, are constants. They are the coefficients of the terms. They're actually not called the base. I don't know why that's on there. So we'll take that off. A sub n through a sub 0 are constants. They are coefficients. The x in this case is the variable. So what you're used to seeing is something along the lines of, say we write a quadratic, x squared plus 3x plus 2. Okay, this follows the same form as a polynomial function because it is a polynomial function. In this case, our a sub n is 1. So we have 1 x squared. The n in this case is 2. And then our next one is a sub n minus 1. That's just telling me that's just the next constant. And our x is to the n minus 1 power. Well, if n is 2, then this should be the 2 minus 1 power, which it is. It's to the first power. And then a sub 0 is our constant. Okay, so that's what you're used to seeing. The n minus 1, the n minus 2, etc. Those are the exponents. Okay, so the only part of this that's going to be a variable is the x. The x is the variable. Every other variable, every other letter you see on here, I shouldn't use variable. Every other letter you see on here is going to be an actual number. X is the only thing that is going to be the variable in our problems. So when we scroll down, we're going to talk about some terminology. A sub n is the leading coefficient. A sub 0 is always the constant term. And n is the degree of the function. Okay, and some degrees have certain specific names, like first degree would be linear, second degree would be quadratic, and then third degree would be cubic, and then fourth degree and fifth degree, don't worry about those. Linear, quadratic, and cubic, those are the names of those functions. They have special names because they're used so often. Okay, and then lastly, we're going to talk about standard form. What does it mean to be in standard form? Well, if a polynomial function is in standard form, that means that it's written in descending order. And you're used to seeing things in descending form, like this quadratic up here, if you look. It's written x squared plus 3x plus 2. If you look, it is in descending order. The exponent is 2. That's the biggest exponent. This next exponent will be 1. That's smaller than 2. It's 1 smaller than 2. And then this last exponent, you could even think of this as x to the 0 if you wanted to, because we know that x to the 0 is 1. So if you want to think you can see that, then that's fine, but usually we just leave that off. So standard form means descending order. We're going to do a couple examples where we're going to list the leading coefficients, we're going to list the degree of the polynomial, and we're going to list the constant. So first I'm going to write the leading coefficients. Now I'm going to abbreviate coefficients. 1 because I usually spell it wrong, and 2 because I don't want to write the whole thing out. So the leading coefficient in this case is the constant or the number that is attached to the largest term, or the term with the largest power. So in this case, the term with the largest power is x to the third, and the constant that goes with that, since there is no number, is 1. Next, we're going to look at the constant of the entire polynomial function. And if your problem is written in standard form in descending order, your constant will be your last term. Or you could think of it as the term that doesn't have an x by it. So in this case, it equals -4. And then lastly, we're going to talk about the degree. And the degree of this function, since the biggest term is a cube, since the biggest term is x to the third, the degree is 3. And it has a special name, and we call this a cubic function. Example number 2. Start with that. Example number 2. We look again, it's in descending order. So my leading coefficient, I'm going to abbreviate, is 4. The constant in this case is 1. And the degree in this case is 2. But the special name for that is a quadratic. Okay, and then our last example, we look, I want to say that the leading coefficient is 3. But don't always assume that the leading coefficient is in the front. If your problem is written in descending order in standard form, then yes, your leading coefficient will be the first number attached to the first term. That is true. However, you have to make sure that your polynomial function is written in descending order. If I scan over this real quick, I see that I have an x to the third, and then I have an x squared. X to the third is my biggest term. So I'm going to rewrite this in standard form, in descending order. So my highest power is x to the third, so I write that first, 2x to the third, and then I'll just go down from there. So plus 3x squared plus 7x minus 1. Now I am in standard form. Now I can see that my leading coefficient in this case is the number attached to my largest term, so that is 2. The constant is -1, and the degree is 3, or cubic. That's the special name we call it. So that's identifying the vocabulary, looking at a polynomial function, figuring out what the leading coefficient, the constant, and the degree is. That's going to help us out when we talk about finding roots of polynomial functions other than quadratics. The last thing I'm going to show you is end behavior. And when we talk about end behavior, we talk about the end of a function. Well, you can't really talk about the end of a function because it goes on and on forever in both directions. This line, this red line, goes on and on forever in both directions. So we can't talk about the end because there is no end. So what we're going to talk about is as we get close to the end. As our x values get really big, as our x values go out this way, get really big, what happens to our y values? What happens to our graph when I look at really big, large values of x? So instead of saying really big every time, I'm going to say what happens as x approaches this number that we have, or this, not even this number, this concept that we have to represent really large numbers, and that is infinity. So we're going to look at what happens when x approaches infinity, and then we're going to look at the exact opposite way when x approaches negative infinity. So if we're moving to the right, we're talking about x approaches infinity, x getting bigger and bigger. If we move to the left, we're talking about x approaching negative infinity, or getting smaller and smaller. So for this first graph, we look, as x approaches infinity of this positive linear function, as x gets bigger and bigger and bigger and bigger and bigger, my y also gets bigger and bigger. So as x approaches infinity, that means that y is also approaching infinity. So if I pick a really big number for x, I'm going to get a really big number for y when I plug that into my function. And the exact opposite is true for when x approaches negative infinity, because as I pick smaller and smaller numbers for my x, my y values get smaller and smaller. So this is as x approaches negative infinity, y also approaches negative infinity. And this is for a positive linear function. Now we look at negative linear functions. So we want to look at what happens when x gets bigger and bigger and bigger. Well, if I picked a really big value for x, I would get a really small value for y. So as x approaches infinity in this graph, y approaches negative infinity. And then the exact opposite of that, as x approaches negative infinity, I look at what values for y I will get. Well, my y values are getting bigger and bigger and bigger. So as x approaches negative infinity, y approaches infinity. Now, if I look at the next one is a quadratic. So I want to look at what happens as x approaches infinity in this quadratic. So if I do x approaches infinity, if I pick some really big number for x, I'm going to get some really big number for y. And likewise, if I pick some really small number for x, I'm still going to get a really big number for y. So with the quadratics, it doesn't matter which way your x is going. Your y still approaches positive infinity. And this is a positive quadratic. On the negative quadratic, as x approaches infinity, as x gets bigger and bigger and bigger and bigger and bigger, my y value gets smaller. So y approaches negative infinity. And the exact opposite, as x approaches negative infinity, as x gets smaller and smaller and smaller, my y values also get smaller and smaller. So if we look at the actual functions for these graphs, if we look at the actual equations for these graphs, I'm just going to call this y equals x, because that's basically what it is. And I'm just going to call this y equals, oh, I wrote x equals. I'm going to call this y equals negative x plus 1. Doesn't matter. Just looking at the x's. And I'm going to call this y equals x squared. And let's call this one y equals negative x squared. It doesn't have to be anything after the x squared. In this case, only the x squared term matters. So here are 4 cases. I have a positive and a negative linear equation, and I have a positive and a negative quadratic equation. And if you look at the end behaviors for each, just take a second to look at those. And then we're going to look at